this is the last part of our major theories section. We're going to talk about two more theories. The first is information processing theory. So information processing theory, otherwise known as IP theory, is based on the idea of computers. So this theory looks at our minds and our thinking as though they're computers. It compares the way a computer stores and uses information with human memory and learning. It does make sense. We designed computers to think like us. We don't know any other way to think. So the terminology and ideas used to describe computers can pretty easily be applied to our own thinking. Inspired by computer memory, programming, the ideas of input and output, etc. So thinking is influenced by neurons, synapses, and neurotransmitters. So this theory takes more of a biological perspective. So the processes of thought. Instead of interpreting the responses of children, as Piaget did, IP theory focuses on the processes of thought. When, why, and how do neurons fire? So the idea of input and output comes in. Input is when something is picked up from the senses. It then goes to the brain where there are connections, memories, reactions, etc. Then there is an output. Maybe we move our hand, we make a sound, etc. So IP theory focuses on processes like memory and attention, and it deals with these ideas of computers. So I have another video for you to watch, but I can't show you it in YouTube because of copyright issues, so please download this PowerPoint and follow the link and watch this monkey business illusion. And then at the end, just think about attention and what you were able to pay attention to. Sustained attention is the ability to tune out distractions and stay focused on the task at hand. So children have to learn how to do something called inhibition, which is inhibiting responses. So it's like blocking your impulses. That's called inhibition. And you have to inhibit responses to irrelevant stimuli in order to sustain your attention on something. Sometimes the distracting stimuli can be internal. It doesn't have to be a sound or a sight. It can be your own thoughts that distract you. Inhibition is controlled by the frontal cortex, and we'll talk about this a lot in this class. The frontal cortex is the last to develop. So if it's what controls inhibition, then no wonder children are bad at it. Their frontal cortex isn't fully developed yet. Closely related is selective attention. This is when there are many things going on and you can focus on just one. Like you're in a crowded room and there are a lot of conversations going on, and you can focus on just the one in front of you. So many children have trouble both with selective and sustained attention because both require inhibition. We're not talking about ADHD here, which is an extreme example of not being able to focus and stay focused. A child can have trouble focusing and not have ADHD. It's just an immature frontal lobe. So now working memory. So working memory is the ability to hold information in your head in the short term. It used to be called short-term memory, now it's called working memory. I have another fun little video here where you can test your own working memory, so I encourage you to try that out. The duration of working memory is the length of time that items can remain, and it's about 30 seconds. So if something enters your head, you can hold on to it for about 30 seconds and then you lose it, unless you do something to keep it going, such as repeating it. So maybe someone reads a phone number to you and you repeat it to yourself over and over so you can go write it down. That's using your working memory. The short-term memory capacity, the working memory capacity, is pretty small. We can generally retain about 5 to 7 pieces of information at a time. So if we can combine representations into bigger chunks of memory, space is freed up. So this is how some people remember long strings of numbers. So instead of individual numbers, group them into bigger numbers. So if I was to say the numbers 7, 5, 1, 4, 6, 9, 2, 3, and then ask you to recite those back to me, you might have a hard time with that. That was 8 numbers. But if I told you 75, 14, 69, 23, it's all the same numbers, I just grouped them differently. Well, now it's only 4 chunks of memory, and you're much more likely to be able to remember it. Think of how people recite phone numbers. They take 10 numbers and group them into 3 or 4 chunks of numbers. So a group of 3, another group of 3, and then usually 2 groups of 2. And that's how we remember things better. So why do we study working memory? Why is it important? Well, we use it for everything in everyday life. We need it to conduct most of our daily tasks, but it has importance for learning too, such as being able to remember instructions or holding all of the information from a problem in your head long enough to figure it out. You need this for like word problems in math. You need working memory to be able to sustain attention. There's a lot of uses for working memory. The good news is working memory can be trained and improved, and if you do a search, you'll find all sorts of ways to train your working memory. So now let's go to long-term memory. Working memory is kind of like the RAM in a computer. Long-term memory is the hard drive space. Okay, so it's where things are stored to be accessed later. So retention is how long you can hold information. 2-month-old babies can remember things for a few days before they forget. But as children get older, they can remember things for longer and longer periods of time. Constant reminding increases the length of retention. It keeps the connections fresh in your brain. In young children, memory is very literal. They repeat things verbatim, so this is like before 6 or 7. Have you ever heard a young child quoting parts from their favorite show or movie over and over again? They will repeat things word for word. There's psychological comfort for them in seeing or hearing something they remember exactly. But in older children and adults, it works a little differently. Their memory's more general. We tend to retain impressions and ideas, so we can remember what the conversation was about, but we can't repeat it word for word. So memory does change as we age. Memory capacity. Unlike working memory, long-term memory has unlimited capacity. As far as we know, there is no limit to how much we can store in our long-term memory. Unlike computers, our brains have unlimited capacity to store long-term memories, and nothing is ever truly forgotten. It just may become hard to access. So here's a little diagram about how memory works according to IP theory. We get a stimuli, it moves into our sensory memory. The sensory memory is very, very short, so you'll quickly forget it unless you pay attention to it. If you pay attention to that, it moves into your working memory. And as long as you keep rehearsing it, it can stay in your working memory. But if you don't rehearse it or encode it, it gets forgotten. Well, if you decide to encode it to long-term memory, it goes here, it gets stored in long-term memory, and then when you need it, you pull it back into your working memory long enough to use it, and then you put it back in long-term. So this is how IP theory says that we use our memory. Now we're going to move on to something called flow theory. So flow. This came from a Hungarian psychologist, I believe. His name is pronounced Mihaly Csikszentmihalyi. Don't worry about ever having to pronounce that or spell that. But he came up with this idea of flow. And this is just working at an optimal level. It's known as being in the zone. This is a state of high concentration and initiative. You're working at a level that meets skills but does not exceed them. Time slips by. It is joyous and productive. You've all probably been in a state of flow before. It's when you're working on something and you're so focused that time just passes you by and you look up and you realize it's been hours and you had no idea. I have a couple of videos here that really explain flow. Please download this PowerPoint and follow these links so you can watch them. And if you're interested in flow, then here's a book, Flow, The Psychology of Optimal Experience, and there's many, many other books. Okay. So just think about what some flow experiences are for you. Okay. Flow is a very, very good state to be in. It's where you learn your best. It's where you can retain your information the best. When you're in a state of flow, your brain is working at optimal efficiency. So the reason I cover it in this class is because flow helps children learn. If you think back to Vygotsky and the ZPD, this flow state is very similar to the ZPD. When you're in a state of flow, it's like you put yourself into your ZPD without the need of the more knowledgeable other. So when you're in flow, you have higher engagement, you're more involved in the task. You have higher concentration, you can stay focused for longer. And it increases your intrinsic motivation. Intrinsic motivation means that you're doing something for its own sake. The desire to do it comes from within rather than an external motivation, which is called extrinsic motivation, which might be something like a treat or a sticker chart or grades at college. So intrinsic motivation is really important. Standardized tests and GPAs are positively correlated with intrinsic motivation, but negatively correlated with extrinsic. That means students who have high intrinsic motivation have higher scores on standardized tests and GPAs, and students who use extrinsic motivation get lower scores. So intrinsic motivation is a very important part of learning, whereas extrinsic might actually have adverse effects to learning. So intrinsic motivation occurs most easily when an activity is enjoyable in and of itself. When you are in a state of flow, you have high intrinsic motivation. And enjoyment of the activity can actually increase students' interest and motivation to learn. So if you can get students into a state of flow, they will learn much, much better. So some of the benefits of flow. Again, refer back to the ZPD. They're very similar. If a task is too hard, you have anxiety. If a task is too easy, you have boredom. Neither are conducive to learning. But if students can enter a state of flow, they learn faster, retain more information, they can work longer, etc. Being completely engaged in something that is meaningful leads to better performance, retention of the material, ability to make connections between other material, etc. Your brain is operating at its peak efficiency and performance. This is the best state your brain can be in. And it's very therapeutic to be in a state of flow too. Everyone should spend at least part of every day in a flow state. When you're in flow, skills are mastered faster, you're more productive, you're more creative. It's a wonderful place to be, and everyone should find their flow activities. So how can we incorporate flow into classrooms? Well, we need to make learning fun and intrinsically rewarding. This is easier said than done. Gamification, student-centered projects, the use of humor, those can all help. We also need to allow more freedom for students to choose their own projects and to be creative. If they make their own choices, they're going to be more involved, have more intrinsic motivation, and are more likely to get into a flow state. We also need to minimize distractions, really give students a place where they can focus without being distracted. And sometimes slower is better. Sometimes moving material fast, children can't absorb it, so they just forget it all anyway. So sometimes if we can move slow and get this flow state, children will remember things for longer. This is one of my favorite quotes of all time. If a child can't learn the way we teach, maybe we should teach the way they learn. The reason I have given you all of these theories, even though it's a lot to absorb all at once, is because all of them try to figure out how children learn and how we can reach them and how we can optimize their learning and their development, which is one of the goals of child development. So that's all I have for this lecture. I know it was very long. If you have any questions about them, please contact me or post them on the discussion board on Blackboard.